Okay, let's jump right into this explainer. Today we're getting highly technical. We're going to mathematically deconstruct exactly how machine learning estimators behave, and we'll be breaking down every single concept, formula, and notation from Professor Tapio Pahikkala's lecture on learning curves and estimator properties in exhaustive detail. If you really want to understand the rigorous underlying theory of how we actually evaluate algorithms, well, you're in the perfect place. Here is our agenda for today. We'll cover estimator consistency and limits, formulating holdout utility, the law of total variance, learning curves and descent, conditional versus unconditional perspectives, and finally, MSE and cross-validation bias. Estimator consistency and limits. Let's start with the absolute bedrock rule of statistics, estimator consistency. The formal definition reads like this. The limit as our total sample size, the absolute value of S, approaches infinity of a specific probability. Now, that probability is the chance that the absolute difference between our calculated estimate, which is theta hat, and the true real-world value, theta, is greater than some tiny margin of error, epsilon. For an estimator to be consistent, this entire probability must strictly equal 0. So translating that pure theory into plain English, it simply means that as we gather more data, our estimators predictably converge towards the real estimand. Consistency guarantees that the law of large numbers actually holds for our estimator. Basically, more data strictly means the estimates get better. As long as we average enough points, we absolutely get this convergence. Moving on to Section 2, Formulating Holdout Utility. To deeply understand how we evaluate a learning algorithm, we first need to define the notation for partitioning a sequence of data, which we'll call Z. We split the sequence into two distinct parts. First, our training set consists of elements starting from Z1 all the way up to ZT. Second, our test data picks up right after that, from ZT+1 up to the size of our required test set, which we denote as K. Now, what's really interesting here is how we define holdout utility as a multivariate function. The crucial point is that the outer utility, function G, relies entirely on an inner utility, K, evaluated solely on the test data. But, and this is a big but, this is subject to a strict condition. Our hypothesis, H, must be the exact output of our learning algorithm, A, when it's fed the training data. This whole setup forms our target estimand, the expected prediction performance of algorithm A when trained on exactly T data points. And this brilliantly illustrates how the formalization maps to real-world practice, specifically for binary classification accuracy. Here, the utility function equals the Heaviside function, applied to the product of the true test label and the predicted hypothesis output evaluated on the test set. The Heaviside function acts as a definitive switch, right? If the product is positive, meaning the predicted label and true label share the same sign and are correct, it returns a 1. Otherwise, it returns 0. This gives us a perfectly clean binary indication of classification correctness for a single test datum. Let's tackle Section 3, the Law of Total Variance. When we look at the formal decomposition of total variance to see exactly where our error comes from, it splits cleanly into two nested components. First, we have the expected variance over the test set, given a fixed training set. Second, we add the variance over the training set itself of the expected test result. We have to account for the noise in drawing the test data and, equally importantly, the noise in drawing the training data. This brings us to a massive realization about consistency. When we analyze consistency as the sample size approaches infinity, the holdout estimator mostly fails. You might be wondering why. Well, because increasing the sample size merely increases the test data. It only ever tests the variance of a single fixed training set. Cross-validation estimators, on the other hand, are mostly consistent because, as the sample size grows, the number of averaged trained test splits scales up too. That means they actually account for that tricky second component, the training data variance. Next up, Section 4, Learning Curves and Descent. Okay, let's map out these mathematical limits visually. Take this specific number, 0.952. This represents a theoretical saturation limit in our underlying probability distribution. Literally, no matter how much data we feed the algorithm, the prediction performance physically caps out at this decimal. Why? Because of the inherent overlap and irreducible noise in the distribution itself. Aside from that theoretical roof, the general heuristic rule we rely on is that more training data improves prediction performance. As our training size t increases, the performance at t+1 is theoretically never worse than at t. For example, With 2,000 data points, we sit at a 0.7 performance. By 6,000 points, we jump to 0.9. And at 10,000 points, we asymptotically approach that strict saturation point at 0.95. But you have to be aware of theoretical anomalies. Proofs, like the famous no free lunch theorems, completely flip this rule. There's also the double descent phenomenon found in deep neural networks. In double descent, the learning curve actually takes a highly counterintuitive dip right in the middle. Performance temporarily gets worse with more data before it finally turns around and improves again. It's a wild exception to the rule.
Let's move to Section 5, Conditional vs. Unconditional Perspectives.
Now, we must split our analysis into two distinct branches to really answer practical research questions. We juxtapose the conditional and unconditional perspectives. The conditional perspective forcefully isolates the analysis to a single realized training set. Our data set becomes one specific, fixed set of points. In contrast, the unconditional perspective treats the entire training sample as a random variable. It computes the expected case across all possible variable training datasets drawn from the distribution. Let's dive into the conditional notation. The bias of our conditional holdout estimator is exactly 0. It is a perfectly unbiased estimator of that single trained hypothesis. Its variance elegantly reduces to just the variance of the fixed hypothesis evaluated on the test set. But what happens if you try to introduce cross-validation here? Honestly, it's heavily discouraged. Averaging over other permutations inherently introduces an unknown bias because the training set shifts, and the variance equation, it becomes an absolute nightmare, potentially even increasing your variance due to split instability. Now let's pivot to the unconditional perspective. Here, our estimand theta is a function of the random variable representing the training set. It equals the expectation over new data of our utility function. Because our holdout estimator is fundamentally unbiased in this view, our full mean squared error equation, the expected squared difference between the true parameter function and our estimator, elegantly reduces straight down to just the expected variance over the training parts. It's a really beautiful simplification.
Finally, Section 6, MSE and cross-validation bias. This brings us to a highly debated and complex question in theoretical machine learning. When we partition data for cross-validation, does increasing the size of that test fold, theoretically, introduce bias against the model we ultimately want to deploy? By decomposing the MSE equation, we find the absolute mathematical truth. The expectation of the squared difference between the true estimand and our estimator breaks into 4 strict terms. First, the squared difference between the learning curve evaluated at the full sample size and at the training size. Second, the constant variance of the full sample estimand. Third, minus 2 times the covariance between the full sample estimand and our estimator. Holdout and CV share all 3 of those components equally. But here is exactly where CV pulls ahead. The 4th term, the variance of the estimator itself. The variance of the cross-validation estimator is strictly less than the variance of the holdout estimator when evaluating the whole sample. However, there is a massive trap hiding in that first term, the learning curve difference. If your test set size k is too large, the remaining training size, t, becomes significantly smaller than your full sample size absolute value of s. This artificially forces the algorithm down the learning curve, artificially lowering the performance metric. This is explicitly defined in the literature as the pessimistic bias. Your estimate basically drifts further and further from the whole sample's true generalization performance. And this leaves us right at the edge of known theory. Years ago, a famous paper in the Journal of Machine Learning Research formally proved a pretty stark negative result. A universally unbiased estimator of cross-validation variance fundamentally does not exist. The math strictly limits us. So, armed with the exact equations for pessimistic bias, total variance, and estimator consistency, which method will you trust when you deploy your very next data set?